Good morning. Welcome to another edition of Chemistry on the Fly with Mr. F. Today we're going to break into a new section we're going to study the chemistry of light. This is going to be part 1 and it's 6.10. So, what is light? Well, it's going to depend on who you ask and what our application is. So, light. If you talk to the Greeks, Pythagoras or Euclid or Ptolemy, back in the BC times, they said that light was a ray. So it would be like that. Now, if you talk to Huygens and Planck in 1690 and 1900, they would say that light is a wave. Okay, would look like that. And then if you talk to Newton and Einstein, Newton in 1704 and Einstein again in 1905, they would say that light is actually a particle. Now, again, it's really going to depend on what we want to do with what we have. So, what we want to look at. So, if we want to look at light as a ray, and we still do this in physics class, when we talk about a mirror, we would say that light, we would use a ray. They could actually call these ray diagrams to see the reflection of how light would relate to a mirror. And then when we talk about in materials, we would use the same kind of ray diagram to determine how light travels through a different material. And then lastly, we would see that we would use ray diagrams to decide how light would react in a lens. So light as rays does have a purpose, and we still use this in physics classes today. Now, light as waves would help us describe color. So if this is going to show my age, but one of my favorite albums when I was a kid was called Pink Floyd, and it was called The Dark Side of the Moon. Now, many of people my age grew up with this album, and you can see though, and I called it an album, you would call it a CD, or you'd even call it just I don't even know what you would call it today, but it would be all digital today. But you can see on the cover, you see a white light coming in and hitting a prism and then breaking down into the various colors. And you probably have heard this before, but our visible light spectrum is called Roy G. Biv, and that's going to help us to remember the order of it. So it's red, orange, yellow, green, blue, and violet. Now, some people put the I in there for indigo, but I skip that one just for clarity, because we really don't know what a particularly indigo color is. So I have this as different waves, and this is what a wave would look like. Now you can see that the wave has different properties. So the red wave has different properties than the violet wave does. And one of the properties would be called the wavelength. And a wavelength is going to be the length of one wave. So you have the length between the two. It's actually a physical measurement. And it's usually measured pretty small, but it would be a physical measurement. And we would learn that we would have another couple terms that we would have would be the crest would be the top of the wave, and the trough would be the bottom of the wave. And then we have another term that we pick up. It's called frequency. Frequency would be how fast a wave actually travels through a point. And it's measured in hertz, and it's actually 1/2. So it's kind of like a rate. Now, the visible spectrum that we just saw is actually part of a bigger spectrum called the electromagnetic spectrum. And here's an example of that. And we go through the different ones, and we've heard most of these before. So a radio wave, there's an old-time radio. I'm not even sure you use the radio waves much anymore. Maybe in your car you might. Microwaves, which you all know what a microwave is. And one of the challenging things that is really nobody's paying a whole lot of attention to, but our phones actually use microwaves. Now, you know we have a lot of protection when we use a microwave oven. We have to have the door closed or it won't work. But we're now putting our phones in our pockets, and they're producing using microwaves to communicate. So I'm not sure how really safe phones are, and there's really no way to tell until we have some time on it, and we'll see how that plays out in the future, especially for you guys who use them much more than I do. Okay, then on the next slide we have an infrared, which is going to show a heat stamp. And then we get into our little section called the visible spectrum, and this is what we just talked about, our Roy G. Biv. And then we go to ultraviolet, which is on the other side, and that is going to be something like cosmic bowling, where you can see that when you put ultraviolet lights on, you can see that the pins and other sometimes white things will become very, very bright. And some fluorescent colors will show up, and that's all due to ultraviolet. Okay, then we have X-rays. Sorry, Homer. Yeah, we know you don't have big brain, but that would be an X-ray. And then the last we would have gamma rays, where we would have a nuclear explosion. So if we look at this picture, this radio wave, microwave, infrared, visible, ultraviolet, X-ray, and gamma, we would see that we have radio waves on one end and nuclear explosions on the other. And as you can imagine, that the energy of these waves would increase as we go from radio waves through gamma rays. And if we look at our visible spectrum, since that's what we're going to focus on in this class, we would see that red colors has less energy than our violet colors. So the red would have less than orange and yellow, and then we'd go all the way up to violet. All right, now we've got to take a look at some of the things that we think we know. And we're going to talk about what happens when we mix colors. So when we talk about paint, we talk about red, yellow, and blue as our primary colors. Okay, and if I want to get, let's say, orange, for instance, I would actually need to take red plus yellow is going to yield orange. And since we just finished up with balancing equations, I kind of wrote this like an equation. This would be technically a synthesis reaction, where I would take red plus yellow and then yield orange. I would do the same thing if I wanted to do green. I would take yellow plus blue is equal to green, or yields green. And if I were to want purple or violet, I would take blue plus red and yield the violet. And then if I took all of my colors, red plus yellow plus blue, and put them all together, now, I don't know if you've done this. When I did this as a kid, I would get some yucky brown, but theoretically, you're supposed to get black. Now, that's nice, but that's not always what's going to happen when we talk about light. Light, in fact, we don't even start with our red, yellow, and blue. We actually start off with red, green, and blue. So RGB for red, green, blue. This is kind of interesting. So what would happen if I take red plus green? Now, typically, if we would do this in paint, we would get a brown color of some sort. But I don't know what we're going to get. When we take blue plus, or excuse me, green plus blue, I'm not sure what we're going to get. And then lastly, if I take blue plus red, I'm not sure what I'm going to get on that one either. And then the last part of this is probably the most interesting one. If I take red plus green plus blue, who knows what I'm going to get there. Right, I found this really cool app online, and it's from a group called PATT, and it's out of the University of Colorado, and they make a whole bunch of really cool simulations. If you ever get a chance and you just feel like playing some different things and see what happens, I would recommend going to PATT to do this. This one's just going to show us the difference between how light works. Now, here's our three colors, red, green, and blue. So if I put my slider up to full red, surprise, surprise, I actually get red. Okay, when I take my full green up, I get green. And this should not be a big surprise here, but when I take my blue up, I actually see blue. Now, one of the things here that's interesting is that this app is actually showing light as particles, just like Newton and Einstein showed. And then we take that information in and we interpret it as these different colors. So let's take our blue back down. Now, let's see what happens when we mix our colors. Now, before, we would take red and yellow and make green, but this time I have red and green. I don't know what I'm going to make, so let's see. Ooh, that's kind of interesting. I said red and yellow make green, but I should have said red and yellow make orange. But so in this case, we have red and green, and we mix those two together in light, and we actually get yellow. So let's take our green down, and let's do the same thing for our blue. Do you want to make any predictions before you do this? You might want to stop the video and make a prediction. Okay, so I have red and blue, and I actually make a pink color. Again, pretty interesting there. All right, I'm going to take red down since the last one we have to mix is blue and green. So I'm going to have blue. I'm going to add some green in here. Ooh, and again, I make something kind of unexpected. I'm making like a periwinkle blue, something like a sky blue, very light blue. All right, well, the last thing we really got to do is to mix all of the colors. Now, when we did this in paint, we came out with a black. But when we do this with light, we actually get, check that out, we actually get white. So when I mix all of my colors, I get white. So the white is the accumulation of light, of all the different colors of light. And on the other side, if I take all of my colors and go down to 0 in all my sliders, I actually get black. So in light, black is going to be the absence of color, actually absence of light. So if I wanted to make a gray, what would I do? Well, just like I would normally do, I would take with the average of the white and black. So I would take my sliders and put them about halfway, and I would actually make a gray color. If I wanted to make a lighter gray, I would think, okay, I'm going to put more or less color in. But this is again the opposite. So if I wanted to make a lighter gray, I could take my sliders and actually move them up, put more light in. And I'm making a lighter gray. If I want to make a darker gray, I actually take my sliders and move them down. Again, kind of a strange option here. Actually, you can see as I'm making these sliders, I'm getting different colors. So here's a darker gray. And just like we talked about before, that if I take all of my sliders back to 0, I'm actually going to get a black. So when we see screens on our whether it's a TV screen or our computer screen or laptop screen, they're actually using this concept to make all of the colors on our screen. So the black background on this screen right now is just shown by the absence of the red, the green, and the blue. All right, so we're back with this color scheme, and we didn't know what we were going to make when we left. So let's check it out. So when we take red and green, we learned that we actually make yellow. We take green and blue, and we actually make like a periwinkle blue. And then if I take blue and red and I mix the light colors together, I actually get a pinkish color. Now the last part was probably the most surprising. When I take my red, my green, my blue, and I put them all maxed out, I actually create white. So that was kind of an interesting thought there. All right, so we're going to take some time and we're going to look at a really pretty picture. Okay, I hope this is your morning today, where we have sunlight and we have some green grass growing in front of us. And we're going to look at some interesting things about light. So the first thing about light is that light travels at 186,000 miles per hour. Now, this is the fastest thing that scientists believe that anything can travel. Now, the interesting part of this is people think that light just travels at 186,000 miles per hour, but radio waves travel at 186,000 miles per hour, and gamma rays travel at 186,000 miles per hour, and all of the ones in between travel at 186,000 miles per hour. So It's not just light that travels this fast. In fact, this is what scientists believe is the fastest thing, the fastest speed in the universe. Now, with that information, light takes 8 minutes to reach us from the sun. Kind of just an interesting thought. So, if light left the sun now, 8 minutes from now, we would actually be able to see it. All right. Another interesting thing about the sun is that the sun emits mostly infrared, visible, and ultraviolet radiation. Now, it does emit radio waves and some microwaves and some X-rays, but the majority of what it emits is actually infrared, visible, and UV radiation. So if we look at our sun and we look at our stratosphere, which is part of our atmosphere, we have infrared. Now our stratosphere actually blocks out most of the infrared that we actually see, or that actually approaches the Earth. So we don't get the infrared rays down to the ground. Now, lucky for us, we do get the visible light, and then we get UVA, and part of UVB. Now, these are the ones that will give people like me sunburn, okay, and then cause bad things to happen to our skin. And so we've got to be very careful of that. And then there is actually another one that's called UVC, and this is the highest part of the ultraviolet spectrum. And luckily for us is that our stratosphere, it's actually the ozone in our stratosphere that blocks out most of UVB and all of UVC. And again, these are the stronger of the ultraviolet radiation. All right, now this picture is kind of cool too because it has grass in it. So one of the questions is, why is grass green? Good question. Now, this is going to be for any object, not just the green grass. I just happen to have green grass here. But for any object, we see the color that is reflected. And then all of the other colors are absorbed. So when we look at our sun is producing a white light, and we'll see this a little bit better tomorrow. And we have our red, orange, yellow, green, blue, violet coming out of the sun, making a white light. And then what is reflected is actually the color that we see. So the red, the orange, the yellow, the blue, and the violet in grass are all absorbed, while the green is what's reflected. Kind of an interesting thought there. All right, another big question would be, in this pretty picture, why is the sky blue? Well, this one's kind of an interesting one. Now, there's a lot of theories on this, and there's some that say that there's more than just one reason, but the bigger reason is that it's called Rayleigh scattering. And this is what happens when light bounces off an object that is much smaller than its wavelength. The higher the frequency colors, such as blue and violet, remember they have more energy, they're going to scatter more strongly than the lower frequency colors, such as reds and oranges. So here's a kind of an example. This would be our nitrogen. Okay, it's just a little atom of nitrogen, or a molecule of nitrogen. Okay, blue light comes in and it's then scattered, and it scatters more on the horizontal. Okay, and then let's look at, for the other extreme, let's look at red. Red's going to come into a nitrogen, and it's going to scatter very little. So what do we actually see in the sky? We're seeing the blue scattering of the blue light, the blue wavelengths, whereas the red is coming more straight through, and we're not really seeing that. Now, you might wonder, well, then why are sunsets red and orange? Well, turns out that the sunlight travels much further through the atmosphere at the sunset. So the blues have already been scattered away, leaving the lower frequency colors of reds and oranges remaining. So that's why we have very pretty reds and oranges and pinks sunsets. And that's all we've got for today for Chemistry on the Fly with Mr. F. And as always, have a great day.